Now we show how to use our project to generate the network structure and corresponding code for the handwritten digit identification task. We first direct to the project directory and run the app.py file. If you are using a terminal, please first activate the virtual environment or just install all the dependency list within the requirements txt file on your local machine. Then we start to run the application. After running the application, and we can direct to the local port 5000 as a direction, and we can see our application is showing in front of us. According to the reference online, there are several modules that we need for the handwritten task. First, we need a linear layer to take the image input. Then we need a ReLU layer to perform the corresponding activation. Then we need another linear layer to make it transform to the lower dimension with inset embedding. And then we need another ReLU layer. And for final, since we want to output image identification that to say whether it's 0 or it's 9, we need another linear layer. And then we transform with a log softmax function. As for final, since we want to train the network, we need a loss to measure the difference between our model output and the actual label that is given in the minis dataset. We need a loss layer like this, and we link them as this. If we miss adding some extra layer in our system, such as adding a batch node to the layer, we can double click it and it will be removed from our system. And then we come to defining the input and output and perform some pre-processing when it comes to the handwriting image. We first need a minis dataset. According to the graph legend in the above, it has a main output and it has a label output as this. We want the label to be the one that measures the loss with the actual output, and we link them with the non-loss. And then we want to have the image that input from the minis and use that to training the network. We first need a flatten operation to say that this. Since the image is two-dimensional, while we just using the linear layer, it should be first transformed to the one dimension, and we link to this. And then we link the flatten output to our linear layer. Before actually generating the code, we need several extra operations. First, we need an optimizer to get the training direction of our model. Then we need a manager. Manager is for training the epoch and perform the device management in our system. As for a manager, we click on the triangle and say we can enter the epoch number that we want our model to train. And the model set path is we just want to save our generated model in the local path of generation. And device name, since we can use the GPU or CPU, we just enter the CUDA. If the GPU is not available, you can just enter the CPU for training. As for our case, we use the GPU for training. And we click on. And we click back, it will say the enter parameter is already there. Please notify that the parameter was all auto-generated by the backend PyTorch API, so it will just link directly to the PyTorch API for this corresponding parameter. Now we're proceeding to the actual parameter setting in our model. First, we have the minis dataset. We can say that we can enter the path for the minis dataset and drag it up for a little bit easier entering. Then there's some parameter that we might need to enter for the minis operation. We'll click on the minis dataset and we enter the parameter in this behavior. There are both sides we can identification and to whether to perform the shuffle or to do the actual training. We can do this like this behavior. As for flatten, we can click on it has the in-place forwarding. That's to say, the in-place forwarding to be true is to we will set the input tensor to be replaced by the output tensor. As for the input, we do not want that, so we set the in-place forwarding as false. Now we come to enter the parameter for the inner layer in our constructed network. We have the linear layer like this, and we can enter the future. According to the reference, since the image is 28 multiplied with 28, the in-place feature will be 7084. As for output feature, we choose the 128. And for the in-place forwarding, since it is already created a new tensor after the flatten, we can just replace with true for the ease of memory loss. As for evaluating it to say whether setting the linear layer to the evaluate mode, that to say not actually training, but we want training. We do not, so we just set this parameter as false and maintain the following as a default. And we click on back. Then we're proceeding. After red loop, we can say it's just evaluating, and without other parameter, we just ignore the red loop. Now we come to the next linear layer. After clicking on, it has the similar setting. Since we already entered the hidden side of neural as 128, we maintain this style. As for output feature, we use 64. As for in-place forwarding, since it's already loaded as internal tensor, we can just use true. And we maintain the following as a default. And then we're proceeding to the last linear layer. As for last linear layer, we want the input feature will be 64 and output feature will be 10. Since we want to identify whether it's 0, it's 1, it's 9, or the related stuff. And as for in-place forwarding, we again set it as true. As for logs of max, we can click on and we enter the dimension just instead of using the -1, we change it to the 1 to use the first dimension to actually perform the log_max operation. And as for the in-place forwarding, we can actually again use true. Then we enter the parameter for the loss behavior, and to say we just maintain this as default is alright. Since we want to train the parameter of this network to actually according to the label that the mini data set that's actually output, and we want there's a parameter in the linear layer, and we just link them with a Matplotlib to the actually input of the SGD layer like this. And now we can see that there is still an extra pole in the SGD. It will be taken as a reference loss according to the graph legend on the below. So we have the loss. We just click that and link to that. There's an additional SGD parameter that before training. We use the learning rate at 0.03 and the momentum at 0.9. Now we actually start to generate the code. We click on generate code. We can see that the code generation is complete. In our backend, we can see there are several code snippets has already printed out to showing that the code generation is success. Then we change to the path that's actually holding this kind of generated model. And we come to the with.ml directory for our project. And we can say there's a static folder. We click on that and it will have the model. And we click on the model, it will have the generated model. At the system model, it has preloaded the structure of the VGG19 as this. Then since we have already generated our model in this behavior, the generate JSON is just holding the parameter that we entered in the front end, while the generation task is containing the OR model structure that we have already entered like this. We can say it's all structured format and with the corresponding indentation and the notification is already. Since there are no identification currently implemented, so we just add some loss identification in this model. We want to first print out the model epoch that is currently in, and also want to print out the running loss. The running loss is for each epoch. As for the end, we add the system like this. Since we already tracked the linked loss as this, so we just want to add this tensor to actually training the loss. After that, we finish. And we want to print out the loss for each epoch. Then we finish the running loss identification and it can be already begin to train. Let's start it. And we can say it's now currently download the minutes dataset, it's all extracting and this kind of behavior. Then it will start to training. We can say the epoch number is already printed out. The running loss is currently around 214.4, and we can see the loss is decreasing. We just wait until the end. Since we have already entered the epoch number as 15, it will actually training the 15th epoch. Now we can say our epoch is finished training. Back to our front end. We now illustrate the block profiling that is working, and we can group the several layers to a block. We choose the linear layer 1, linear layer 2, and linear layer 3 to group them as a block. We can say this, and we can say there's a block is already generation, and we perform the same step as the code generation before. Since we have already entered the input for the corresponding block, we just click on the generate code. I can say the generate code is already complete. Come back to the generated model and the corresponding Python file is generated. We can see there's actual lines in the block 1, block 0 is already to pending for our profiling. Then we start running our model again to say whether the actually profiling is working. We just wait the data set to be loaded. Since for this time we did not enter the running loss monitor, we can say there's a block 0 profile is generated under the same generated model. We just click on that. It will show that the corresponding data that it's showing.